Hello, welcome to a video on, I sound like a TV presenter. Well, this video is going to be on differentiation for P2, so P2 differentiation. We're going to start looking at increasing and decreasing functions, then we're going to look at stationary points and how we find them, how we decide what type of stationary point they are, whether they are a maximum or a minimum. So that's what this video is going to be about. I'm going to get straight into it because it has the potential to be quite long. There's a lot of stuff in here. So increasing and decreasing functions. So basically, if we're looking at this part first, for a function to be increasing, it means that the gradient is always at least 0. So when we differentiate it and we have a gradient function, it's always above 0, equal to or above 0. It would be strictly increasing if it is greater than 0, strictly greater than 0, not equal to. Or basically saying that the gradient is always positive. If it's equal to 0, then our line would be horizontal. I don't know what I'm doing. It would be horizontal. It would be like that. It would be our gradient would be horizontal. Which technically is still increasing, but if we were strictly increasing, then it has a positive gradient, which means it is the curve is going up, is increasing. Depending on the type of function you are looking at, so you could have something like this, which is a cubic graph, which is increasing and decreasing in certain intervals. So first we have this part of the graph, which is increasing. The gradient would be positive there. For x is less than or equal to 2. Is it less than or equal to, or is it just less than? Yeah, less than or equal to, because obviously the gradient here, this is a turning point, the gradient changes. So the gradient would be 0. So it's increasing for x is less than or equal to 2. Now in this middle part, in this interval here, it is decreasing. The gradient would be negative, and that is x is between 2 and 4. And now again, because the gradient would be 0 at those points, we do include 2 and 4 in that. So 2 is less than or equal to x, less than or equal to 4. And then it goes increasing again for the rest of the graph. So this part is increasing for, although what was that word supposed to be? Increasing for x is greater than or equal to 4. So depending on the type of curve you are looking at, the type of curve you're interested in, there could be parts of it which are increasing, parts of it which are decreasing, which leads to turning points and stationary points, which is what we're going to look at later on in this video. We could write, there's a little bit of notation there at the bottom. We could also write f of x is decreasing in the interval 2, 4 using square brackets. The square brackets represent all the real numbers between a and b inclusive of a and b. So basically it's just a different way of writing this inequality. We could use a square bracket. Just a bit of notation, not massively important, but just in case you see that, you understand what it means. So have a look at some examples here. We've got to show that the function f of x is x cubed plus 6x squared plus 21x plus 2 is increasing for all real values of x. So the first thing we want to do is differentiate it. So we have the gradient function, because what we're interested in is where the gradient is positive or negative if it was decreasing. So we need the gradient function first before we can determine whether the gradient is always positive, always negative, or whatever. So differentiate it first. Remember, we're bringing the power to the front and reducing the power by 1. So we get 3x squared plus 12x plus 21 is our gradient function. Because the gradient function is a quadratic, to show that it's always positive, the best way to do that is to complete the square. So we're going to complete the square of this by getting rid of that. We're going to factorize out that 3 first to make it easier. We can't just divide by it because what we have is an expression. It's not equal to anything. So we can't just divide by 3 and it disappear. We have to factorize it out. Then we're going to complete the square. So we get 3x plus 2 squared minus 4 plus 7. Simplify, and then I'm going to simplify it first, and then I'll multiply that 3 in. Minus 4 plus 7 is positive 3. And then I'm going to multiply that 3 back in. So I get 3x plus 2 squared plus 9 is the completed square form. Now, because the bracket part is squared, that has to be positive. X plus 2 squared is always greater than or equal to 0 for any real x, for any value of x. Therefore, if we multiply it by 3, it's still positive. And if we add 9, it's still going to be positive. So for any real value of x, the expression, the function we have is always greater than or equal to 0. So that means that f of x is increasing for all values of x. Okay, I hope that makes sense. So steps that we did, we differentiated it to find the gradient function, and then we showed that the gradient function is always positive no matter what value of x we put in there, because we've squared the bracket part, because we've squared the x part essentially. Even if we put a negative value of x in there, once we square it, it becomes positive. We're then multiplying it by a positive number, adding on a positive number. So all of that, it still gives us a positive result, meaning that our function, our original function from the question here is increasing for any value of x. Find the second question is similar, obviously, but slightly different. So find the interval on which the function f of x equals x cubed plus 3x squared minus 9x is decreasing. So again, the first step's the same. We want to differentiate this to get the gradient function. And that would be 3x squared plus 6x minus 9. We still have a quadratic. We want to put it less than or equal to 0 because we're trying to prove that it's decreasing. We're trying to prove that it gives us we're trying to find the values where it gives us a negative answer. So we're going to put 3x squared 3x squared plus 6x minus 9 is less than or equal to 0. Now, because it's an inequality, we can divide through by the 3. We don't have to factorize it out. We can actually divide through because we have both sides of an equation or an inequality. So divide through by 3 gives us x squared plus 2x minus 3 is less than or equal to 0. Divided by 3 is still 0. And then we can factorize it. It's a nice easy one to factorize. We get x plus 3, x minus 1 is less than or equal to 0. So x, if I do a quick sketch just to show where we're looking at, it's a quadratic inequality. It's a positive quadratic, so it looks something like that. Terrible. Actually, it's not. This would be negative 3. This would be 1, 1, positive 1. And we are looking at where it is less than 0. So we're looking underneath the x-axis. So our solution is x is between minus 3 and 1. Therefore, f of x is decreasing in the interval. I'm trying to write when I'm speaking the next part. Is decreasing in the interval. And if we use the notation we mentioned before, my writing's terrible today. Minus 3, 1. Using square brackets. Yeah, so again, so for increasing, we're putting it something greater than 0. For decreasing, we're going less than 0. And we're putting our gradient function, our differentiated function, either greater than or less than 0, depending on what we're trying to find. I hope that makes sense. We're going to keep going and look at stationary points next. So a stationary point is essentially where the gradient of the curve is equal to 0. If we look at that on a graph, it looks something like this. So here at the top, at that point, if we show it with an actual coordinate, at this point, the gradient is equal to 0. That is a maximum point because the gradient is increasing, it goes to 0, and then it starts to decrease. That is a maximum stationary point, a maximum turning point, a local maximum. It's called a local maximum because it's the function's biggest input kind of in that vicinity, so in this part of the graph. It sometimes might have a global maximum, so like the maximum output across the entire function, but this particular function wouldn't have a global because it just keeps going on and on to infinity. It has a local maximum kind of in the middle of the graph, but you're never actually going to get one particular value that is a global maximum because this part of the graph, where's my pointer, is just going to keep increasing to infinity. And same with a local minimum. It's not going to have a local minimum because it's going to go down and down and down and down for infinity, into negative infinity. I hope that makes sense. Again, just a bit of notation, not massively important, but just things that are nice to know. So we have maximum and minimum points. So a local maximum is the largest point, the biggest point, the highest point on the graph, and local minimum is obviously the minimum point on that graph, which again is where the gradient is equal to 0. So find the coordinates of the turning points of this graph, y equals x cubed plus 6x squared minus 135x. Turning points, so again, we're going to have to straight away differentiate. So dy by dx. Notice how I'm switching between notation. So when I differentiated on these questions, I used f dash of x, only because that was how they gave me the function initially. They gave me f of x is equal to. So when I did my differential function, I did f dash of x. For this one, they've given it in terms of y. So when I'm differentiating, I'm putting it dy by dx. They mean the same thing. You can, kind of use whichever, but it kind of makes sense to keep it in the same form that they've given it and give you it in the question. So if they've give you in terms of y, we do dy by dx. If they give you it in terms of f of x, if they give you it in function notation, so f of x, then we use f dash of x to show that we've differentiated. But they mean the same thing. I'm not doing anything different. So differentiate my y gives me 3x squared plus 12x minus 135. And I am looking at where it is equal to 0. I'm looking for the points on that graph where the gradient is equal to 0. So I am going to put, I don't want to run out of space, I'm going to start it over here. 3x squared plus 12x minus 135 is equal to 0. I can divide through by 3 to make that easier. Again, now it's an equation. I can actually divide both sides by 3. I get x squared plus 4x minus 45 is equal to 0. Factorize it. It factorizes nice and easy. Two numbers that multiply to make negative 45 and add to make 4 are positive 9 and negative 5. And so my x values are x equals minus 9 or x equals 5. Once I have that, I then need to find the actual coordinates. So I know the x points, where the maximum and minimum are, or where the turning points are. But I need to find the actual coordinates, which means taking these values and putting them back into our original function. Not back into the differential function, because that's just going to give us 0. Because that's what we've just solved. If we put negative 9 back into our dy by dx, all we would get is 0. What we need to do is take it and put it back into our actual function of the line of the curve and find the corresponding y coordinate. So when x equals, if we start with minus 9, when x is minus 9, y is minus 9 cubed plus 6 minus 9 squared minus 135 times minus 9, which gives me 972. That's quite big. I wasn't expecting it to be quite as big as that. And when x equals 5, y is 5 cubed plus 6 5 squared minus 135 times 5, which gives me negative 400. So my two coordinates are minus 9, 972, and 5, negative 400. So those are the two coordinates of my turning point, and I've fully answered that question now. So be careful of that. Make sure once you found your x values, you use them to find the corresponding y, so you actually have the coordinates, because that is what the question has asked for. Find the coordinates of the turning points. Okay, find the least value of f of x equals x squared minus 4x plus 9. I'm going to show you two ways to do this. The first way works for any type of function. The second way only works if our function's quadratic. So definitely pay closest attention to the first method, because you can use that whenever. Method 2 is just a bit easier for a specific quadratic function. So find the least value of f of x equals x squared minus 4x plus 9. Differentiate it. I'm using function notation. So f dash x is 2x minus 4. I'm putting that equal to 0 because my least value is going to be a turning point, a minimum turning point. So when 2x minus 4 equals 0, if we add 4 across, divide by 2, x is equal to 2. So find the coordinate, the corresponding coordinate, the corresponding y coordinate is what I'm trying to say, by substituting 2 back into my function. So f of 2 is 2 squared minus 4 times 2 plus 9 gives me 5. So 5 is the minimum value is the least value of that function. And we get 5 when we substitute in 2. The other way to do it is by completing the square. Now again, we can only complete the square if the function is a quadratic. So this only works for a quadratic function. If we complete the square, we get x minus 2 squared minus 4 plus 9, which is x minus 2 squared plus 5. And again, we can see that the minimum value is remember when we complete the square, and it literally tells you a turning point of a quadratic, it tells you where the maximum or minimum point of the graph is by reading off what the y value is. So the minimum value is 5. And this happens by taking the opposite sign of x. So it happens when x is equal to 2. We kind of touched on that. Well, we went over that in P1. It's also something we did in IGCSE. But it's, like I say, up to you which method you use. This first way will work regardless of the type of function you have. Method 2, this second way only works if you have a quadratic. Up to you which one you prefer. Find the turning point of y equals root x minus x. So we want to again differentiate it. The first thing I'm going to do is change that root into a power. So it's x to the power of a half minus x, and then I'm going to differentiate. Again, noticing that I'm keeping the notation the same. I was given it in terms of y, so I'm given my differentiated form of function in dy by dx. So I get a half x to the power of negative a half minus 1 is dy by dx. I'm trying to find the turning point, so I'm putting this equal to 0. So half x to the power of negative a half minus 1 equals 0. So a half x to the power of negative a half equals 1 by adding that one across. I'm going to multiply by 2 to get rid of the half. So x to the power of negative a half equals 2. And then I'm going to rewrite this in terms of root x. It's just easier. Personally, I find it easier to calculate with. So 1 over root x, power of negative a half. The negative makes it 1 over a half is square root is equal to 2. By doing a bit of cross multiplication, I get a half. So dividing by 2, multiplying by root x gives us a half is root x. And then by squaring both sides, I get a quarter is equal to x. Now I know my x value, I need to find the y. So when x is a quarter, y is the square root of a quarter minus a quarter. So a half minus a quarter, which is just a quarter. So my turning point, the coordinate of the turning point is a quarter. Same thing. Turning points, the key thing to remember is that a turning point, a stationary point, no matter what terminology they're using to describe it, it always means that the gradient is equal to 0. So differentiate, put it equal to 0, solve it. Find x, put your x value back into your original function to find the corresponding y value. That's the key steps each time. The only thing that changes is the function that you're differentiating, and that can be more or less complex depending on how nice they're being in the exam. But yeah, that's the only part that changes. The actual process is the same each time. Differentiate, put your dy by dx equal to 0, solve that equation, and then put your x into your original function to find the corresponding y value. That's it. There's a third type of stationary point. I'm tempted to maybe stop this here and put it into a second video because this is going to be really long and it'll just make it difficult to upload. Yeah, I'm going to do this separately. So I'll do points of inflection separately. So this video is just increase and decrease in functions and stationary points, turning points, and we will do points of inflection in the next video. Again, I will post these videos. There'll be a series of videos alongside the PowerPoint so that you can do the test your understanding questions and the exercises as well, to just make sure that you're understanding, and let me know if you have any questions. Okay, thank you for watching. Yeah, see you in the next video.